Okay, so for those who want to know how this actually works, I think this is fascinating. So this particular encoder is made by a company called Micropulse, or actually Baluf, if I'm saying that right, and it's the Micropulse version. And if I slide this off, there's nothing physically connecting it. It kind of seems like magic the way it works. But in this little nubbin on the end here is a magnet. And the way this is built, there's a cavity in here, a resonance cavity. It sets up a standing wave, and that standing wave is disrupted by this magnet being placed within it. It can detect the change in frequency based on that standing wave distance by where the magnet is located to within like a micron, which is incredible. There's a big circuitry inside here. So I read through reverse engineer the part number, and I figured out the BTL is obviously the Baluf Micropulse series. The S means it does SSI, or synchronous serial interface output. The 102 tells me it uses 24-bit output, leading edge. And then the M305, the 305 is the distance in millimeters, which works out to be 12 inches for scale. P series, and then, numbers. This one represents what style it is. Like if it's a rectangular or a round side, and if it has what kind of connector, flying leads, or tail on it. Speaking of which, tail comes on it, and then I figured out these wires, and I had to find a pin out which colors did what, and I'm feeding that into Arduino. I'm only using 3 wires. I have a clock, I have a data in, and I have a ground. I have to feed the sensor 24 volts DC, so I'm using a big power supply to actually power it, and then everything else is done TTL at 5 volts. So basically, I feed it, I hold the clock high, and then I pulse down, and then pulse up, and then pulse down, and then pulse up. So from 5 to 0. When I pulse down on that first one after being held high for more than 20 milliseconds, the sensor will feed out the first data bit. And then I just keep pulsing the clock from high, low, high, low, high, low, and it keeps feeding each of the 24 bits of data out, representing that large 24-bit number. And once it's done, I stop and I let it go high again for 20 milliseconds, and then it starts over again, and I'm able to get that bit stream back again. It's kind of a neat synchronous communication system, again called synchronous serial interface, or SSI. It's used a lot in industrial automation. From there, I'm using shift in Arduino to read in those data bits and then convert it to a unsigned long data bit. And then that comes apart down here as this number down here. So as I slide this number, you can see it read, and if I get closer to 0, there's about as close as I can get. So right now that 1 represents me being 5 microns from 0. And then you can read all the way up. So 60,000, I did the math, about 60,000 there represents exactly 12 inches. So that's the accurate range of the scale. And again, I noticed they give you an extra inch of play in there, which is kind of cool. And then there's a 0 set here. But I noticed when I slide the sensor back that the 0 is a little bit buried under the top edge of this. So just things I discovered. But that's the technical details on how it works. And I just need to wire in a probably an I2C display on the output that's large enough to be able to read out those large of a number up to 60,000. But I'm also may convert it to the micrograms and do the math internally so I don't have to do it externally, which would be really cool. So make sure you stay tuned. Thanks for watching.